Hello, my dear students. Welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch all my videos on my channel. Today we are going to start the discussion on. Before analyzing the flow conditions, we have to classify the type of flow. Flow is classified based on time as the criteria and space as the criteria. If you are considering time as the criteria, then we have to consider the variation of the flow characteristics with respect to time. So based on the time, we can classify the flow as steady flow and unsteady flow. So in steady flow, the flow characteristics, that is the flow depth and flow velocity, are constant with respect to time. Whereas in unsteady flow, the flow characteristics are varying with respect to time. So in steady flow conditions, the flow is continuous and the continuity equation is valid. But if you are considering space as the criteria, the flow is classified into uniform flow and non-uniform flow. So in uniform flow, these flow characteristics, that is flow velocity and flow depth, are constant along the length of the channel. Whereas if it varies with respect to length, then it is termed as non-uniform flow. So in more general, we can classify the flow as steady uniform flow and steady non-uniform flow. Similarly, we can classify the flow as unsteady uniform flow and unsteady non-uniform flow. In steady uniform flow and non-uniform flow, the flow is continuous, so A1 V1 equal to A2 V2 is varied. Whereas in unsteady uniform flow and non-uniform flow, since the flow variables are mutually dependent, we cannot directly use this equation. Non-uniform flow means the flow characteristics are varying with respect to space. So how this flow characteristics are varying with respect to space, whether it is a gradual variation or a sudden variation, based on which we can classify this non-uniform flow as gradually varied flow and rapidly varied flow. So this type of non-uniform flow that is occurring in both steady condition as well as in unsteady conditions. So the figure shows the different conditions of flow. So this figure represents steady uniform flow condition. So you can see that flow characteristics are not changing with respect to space and time. So if you are measuring the flow characteristics at this section or at this section, it is same. Whereas if you are considering this case, which is represented as unsteady uniform flow. So in unsteady uniform flow, it is a very rare case to occur, but here you can see that this is one flow conditions, so or this is at a particular time. So at this particular time, it is maintaining the uniformity. When the time changes, it is maintaining the uniformity, but it is different from the first one. And for the next time, it is maintaining the uniformity, but it is different from the other two. So here you can see that uniformity is maintaining in a particular time steps. In the second figure, which represents steady non-uniform flow. So the figure shows a tank that is holding water. So gate at the downstream side opens partially. So water is allowed to flow through this opening. So here the flow variation is so sharp, then it is allowed to flow through the channel. For this small portion, the flow variation is so sudden, so it is represented by rapidly varied flow. Whereas from this portion to this portion, the flow varies gradually. It is represented by gradually varied flow. So because of this wear, a sudden change in flow depth occurs here. So indicated by rapidly varied flow, followed by gradually varied flow. Then here you can see a sudden drop. So the flow conditions are changing suddenly. So it is represented by rapidly varied flow. Then it is allowed to flow through the channel gradually, represented by gradually varied flow. And here you can see that a sudden drop in the channel bottom. So there is a rapid variation represented by rapidly varied flow. And again it is follows gradually varied flow. So this figure represents the combination of rapidly varied flow and gradually varied flow. Here also the continuity equation is valid. So if you are taking the different sections, A1 V1 equal to A2 V2, that is valid because it is steady non-uniform flow. You can also note that whenever this rapidly varied flow occurring, it is occurring for a short stretch, whereas gradually varied flow that is occurring for a long stretch. Third figure, which indicates unsteady, non-uniform flow. So this figure represents the entry of the flood wave to a river. It is a gradual occurrence represented by gradually varied flow, whereas here entry of the surge to a river following the opening of the navigation lock. So it is represented by rapidly varied flow. So for analysis of the flow, we should identify the type of flow. In this session, mostly we are dealing with steady uniform flow and steady non-uniform flow. In the next section, we can discuss about the uniform flow conditions. So what is uniform flow? During uniform flow, the flow characteristics are constant along the length of the channel. That means flow depth and flow velocity are constant along the length of the channel. So the figure shows a flow segment of an open channel enclosed within the section 1 and 2. So section 1 and 2 is at a distance of L apart, and y1 and y2 are the depth and v1 and v2 are the velocity. Since it is uniform flow conditions, y1 equal to y2 and v1 equal to v2. So if you are balancing the total energy between the section 1 and 2, then y1 plus v1 square by 2g plus z1, that is equal to y2 plus v2 square by 2g plus z2 plus hf. Since y1 equal to y2 and v1 equal to v2, so this y1 and y2 get cancelled. Similarly, v1 square by 2g and v2 square by 2g. If you are rewriting this equation, then z1 minus z2, that is equal to hf. So if you are dividing LHS and RHS by L, then z1 minus z2 by L equal to hf by L. So what is z1 minus z2 by L? It is represented by difference in bed level divided by L, that is the bed slope S0. So hf by L indicate the slope of this total energy line. Slope of the total energy line is indicated by SF. So uniform flow condition means bed slope S0, that is equal to SF. So the uniform flow occurs when the resisting force is get balanced by the weight component in the flow direction. So in this section, we are going to discuss about the uniform flow equations. There are different number of equations are available, among which we are discussing this equation. So the figure represents the flow segment of an open channel between the two sections 1 and 2. Theta is the bed slope. Weight of this flow segment, that is ABCD, that is acting downward, which is equal to rho g into AL, where A is the area of the flow section and L is the length of the segment. And weight component in the direction of the flow, that is equal to rho g AL into sin theta. Weight component in the flow direction is resisted by the resisting force due to the surface roughness. It is opposing this force. The resisting force that is acting in the opposite direction. Since it is uniform flow, y1 equal to y2 and v1 equal to v2. So since y1 equal to y2, the pressure forces F1 and F2 both are equal. So the only forces that's acting in this flow segment is, one is weight component in the direction of the flow and other is the resisting force which is opposing the flow. So uniform flow condition, that is equal to S0 equal to SF. So weight component in the direction of the flow or the force causing the flow, that is equal to rho g into AL into S0. Sin theta is represented by the bed slope S0. And the resisting force that is acting on this wetted surface area equal to tau into P, that is the vectored perimeter, into L. So this is the vectored surface area. Since the pressure forces F1, that is equal to F2, because y1 equal to y2, by applying Newton's second law of motion, rho g AL S0, that is equal to tau into PL. So in uniform flow condition, rho g AL S0, that is equal to tau into PL, or rho g AL S0 minus tau PL equal to 0. So if you are simplifying, tau equal to rho g into A by P into S0. But A by P, that is equal to R, that is hydraulic radius. So tau equal to rho g into R into S0. So we have learned previously that tau equal to F by 8 into rho v square, where v is the flow velocity and F is friction factor. So if you are replacing this tau by means of F by 8 into rho v square, Then expressing in terms of velocity, then we can write v square equal to 8g by f into r into s naught, or v equal to c into root of r into s naught. So v equal to c into root of r into s naught. So this equation is called Chezy's equation. C is Chezy's constant. So c, that is equal to root of 8g by f. So if you know the velocity, then we can calculate the discharge as area into velocity. So where A is the cross-sectional area of the channel. So another equation which is used for the computation of velocity, that is Ganguillet-Kutter's formula. So in this equation, they are using the same equation as v equal to c into root of r into s naught, but c is defined by Kutter's constant, that is equal to 23 plus 0.00155 by s naught plus 1 by n divided by 1 plus this term multiplied by n divided by root r, where r is hydraulic radius and n is called a roughness coefficient, that is called Kutter's n. So by replacing this c in terms of this constant, then that equation is called Ganguillet-Kutter's formula. So based on that, we can find out the velocity, and multiplied with the cross-sectional area of the channel will give you the discharge in the uniform flow conditions. Another equation which is used for the computation of velocity, that is Manning's equation, which is represented by 1 by n into r raised to 2/3 into s naught raised to half, where r means hydraulic radius a by p and n is Manning's roughness, or it is called rugosity coefficient. So p is the vector perimeter. And Chezy's equation for the computation of the velocity v equal to c into root of r into s naught. If we are equating these two equations, then we can establish a relationship between this n and c. So if we are equating Manning's equation and Chezy's equation, then we can relate c equal to 1 by n into r raised to 1 by 6. C is Chezy's constant and n is Manning's roughness value or rugosity coefficient. In most of the channels, these n values are available. The variation is based on the smoothness of the channel. So if it is a cement concrete finish channel, n value equal to 0.015, whereas for unfinished cement surface, the value of n equal to 0.017, and it increases drastically for earth channel, which is equal to 0.035. So whenever we are dealing with the problems, these n values are available. So we can directly calculate the velocity. Correspondingly, we can calculate the discharge as Q equal to area into velocity. So in this class, we have discussed about uniform flow conditions and the derivation of uniform flow discharge equations. We also defined the type of flow based on time as criteria and the phase as the criteria. So there are different shape of the channels are available. So we should know the geometric elements, geometric parameters for each shape for analyzing the flow characteristics. So in the next section, I am going to discuss about for the time being it is enough. Thank you. Your SumamMiss.